Welcome to ECE 302. This is Lecture A5 on wide sense stationary random processes. I'm Professor Stanley Chan. Today we're going to look at a very special type of random processes, which is the class of wide sense stationary random processes. If you recall our previous lectures, a random process x of t is a function with a random index psi. We can define its mean as a function of time, and we call this as the mean function. We can also define a thing called the autocorrelation function, which is a two-dimensional function in terms of two time indexes, t1 and t2. t1 specifies the starting point and t2 specifies the end point. And so if you have a function and then it is a random function, essentially you're looking at one point here and then the other point there. You're looking at this pair of random variables and you're looking at their correlation. We mentioned that the mean function and also the autocorrelation function, they are extremely important quantities to quantify a random process. Now, of course, any random process will have a mean function. It will also have a autocorrelation function. But there are some random processes where the autocorrelation function and also the mean function will take some very special forms. And wide sense stationary processes is one of those. So what is wide sense stationary random processes? A random process x of t is said to be wide sense stationary with a shorthand notation of W as S if the following two criteria are satisfied. The first criteria is that the mean function is a constant, meaning that it does not change over time. The second criteria is that the autocorrelation function, which originally is a function of t1 and t2, meaning that you need to specify the starting point and also the end point. It is a two-dimensional function. However, this two-dimensional function is simplified to a one-dimensional function, where this t1 and t2 will always take the form of t1 minus t2 or t2 minus t1. So what is this? If you recall an autocorrelation function, it is a two-dimensional function. So there are autocorrelation functions like the ones that we have seen in the previous lectures, where you can draw the autocorrelation function for a amplitude and changing cosine function, and then this is the autocorrelation function. And if you look at this, this function cannot be written as a time difference between t1 and t2, versus another example where we have this banded diagonal matrix. This is the random phase function, and then you can see that this case you can write this Rx as t1 minus t2. So there are some random processes which can satisfy this property, whereas some other processes do not. So we are going to go back to these two examples and look at why they can be written in this form, and why with this picture here, where you have a bunch of circles, that doesn't allow you to have this wide sense stationary process. And here, this function that has a very beautiful banded diagonal structure, that will allow you to have a wide sense stationary process. So at this point, you may wonder, why do we care about wide sense stationary processes? It turns out that wide sense stationary processes, they are very nice processes. Think about what are you going to do with a random process as you transmit this random process through a linear system. For example, you're doing some kind of filtering of a speech signal, and then the system that you're encountering will be a linear system. You're doing convolution of this speech signal. How are you going to look at the randomness of the filtered speech signal? In this case, if you know that the signal is wide sense stationary, you can apply all the beautiful tools that you have learned in the Signal and Systems course and apply them to here so that you can do the convolution. And similarly, you can also apply the Fourier transform to the signals. And you can do the Fourier spectral analysis and then to look at the signals. So those are extremely useful techniques, but those techniques can only be enabled if you have wide-sense stationary processes. So let's spend the following few slides to understand more about this wide-sense stationary processes. But before we do that, I also want to mention that this definition here can also be changed to look at the autocovariance function instead of the autocorrelation function. This is because the autocorrelation function and autocovariance function is related to each other by this equation, where Cx of T1 and T2 is written as Rx of T1 and T2 minus mu x at T1 and then mu x at T2. And so if mu x is a constant, as I am specified in the definition of wide-sense stationary processes, then of course any property that you have from Rx can be translated to the properties of Cx. And so you can define wide-sense stationary processes using both Rx or Cx interchangeably. The other comment here is that if you have a wide-sense stationary process, then your autocorrelation function, which is a function of T1 and T2, this is a two-dimensional function, if you can write it as T1 minus T2 or T2 minus T1, you can really just simplify this T1 minus T2 as a function of tau, where tau is the time difference between the two timestamps. So if you recall what is the Rx at T1 and T2 is defined as the expectation of x of T1 and x of T2. And so now if I say that this T1 equals to some time t plus some offset tau, and T2 is some time t, well then this T1 minus T2 is essentially just tau, because you put the T1 as t plus tau and T2 is the t. You take the difference is always tau. Okay, and so we can write this Rx of T1 minus T2 as Rx of tau to just simplify the notation. Okay, so let me go through a couple examples with you to make sure that we understand how to calculate the wide-sense stationary processes. All right, so the first example is the following. Let us try this random process. X of t equals to a times cosine omega t. Let's just do cosine omega t. Okay, and where a is uniform in 0 and 1. So we ask, is this random process a wide-sense stationary random process? So we know what is the mean function. So the mean function of this random process is just the expectation of a cosine omega t. And since cosine omega t has nothing to do with expectation, you can pull them out, and so you have this expectation of a and then cosine omega t, and that will give you 1/2 of cosine omega t. So that is your mean function. Similarly, you can also calculate the autocorrelation function. The autocorrelation function is expectation of a cosine omega t1 times a cosine omega t2, and you can do the calculation. And you can show that this is going to be 1/3 of cosine omega t1 and then cosine omega t2. Okay, so we ask, is this random process x of t a wide-sense stationary random process? So we can go back and check the definitions. The first criteria is that the mean function has to be a constant for all time stamps t. So we look at this equation here. The mean function, does it change with time? Well, actually the mean function indeed changes over time. As your time t changes, this mu t also changes. You can plot a diagram and convince yourself. If this is the random process, you can have multiple random realizations. So these are the random realizations because it's a cosine function with a different amplitude. The mean function would be somewhere in the middle. Okay, so this is the mean. This is your mu of t, mu x of t. This mu x of t indeed changes over time. If you are at this time stamp versus you are at this time stamp, you are looking at two different values. And so this mean function changes over time. So at this point, you can already say that this changes over time. And so you can conclude that this function here is not y-sense stationary. Okay, we don't even need to check the autocorrelation function, because if the mean function changes over time, it's already violating the first criteria. Okay, and therefore a random amplitude cosine function is not a y-sense stationary process. Let's try another example. The other example is x of t equals to cosine omega t plus theta, where theta is uniform distributed from 0 to 2 pi. So what is this function? Well, this is a random phase function. It's a function that we have seen several times before. Let's calculate the mean. The mean function is the expectation of cosine omega t plus theta, and this is just the integration of cosine omega t plus small theta, and of course you have the PDF of the theta, and then you integrate with respect to the theta. Now this f of theta is what? This f of theta is 1 over 2 pi. So you integrate this thing, which is the integration from 0 to 2 pi, then you have 1 over 2 pi, and then you have this cosine omega t plus theta d theta. You integrate this quantity here, and you know that this is 0. Okay, because you're integrating over one period of this cosine function. So you get 0. Now, how about the autocorrelation function? The autocorrelation function is the expectation of cosine of omega 1 plus theta times the cosine omega t2 plus the same theta again. So you can do the calculation, and you can show that this is going to be 1/2 cosine of omega of t1 minus t2. Okay, so I'm skipping the calculation, which you can go back to the previous lectures and find out. So let's examine this random process and see if it is a y-sense stationary random process. Let's look. Well, the mean function is a constant. Yes, indeed it is a constant. It is a constant. It equals to 0 all the time. If you try to plot the function, this function would look like the following. You have this random realization 1, random realization 2, another random realization, and so on. What is the mean function? Well, the mean function is just 0, okay, as what we have calculated. You ask, does it change over time, t? Well, no matter which time you are looking at, here or there, is always 0, and therefore it is a constant. And then, so that means the first criteria has been satisfied. How about the second criteria? The second criteria says that I need to look at the autocorrelation function, which is a function of t1 and t2. I want to check whether this can be written as Rx of t1 minus t2. Is that true? Well, according to our calculation, this is indeed the case, where this autocorrelation function as a function of t1 and t2 can be written as a cosine of omega t1 minus t2. So in other words, as long as I have a t1 minus t2 known, I do not really need to know when do I start and when do I end. For example, t1 equals to 1 and t2 equals to 5 versus t1 equals to 2 and t2 equals to 6. These two pairs of numbers will give me the exact same value of this autocorrelation function. In other words, Rx of 1 and 5 is the same as Rx of 2 and 6 because I really just cared about the difference between these two time points. I do not care about their absolute starting point and their end point. I only care about how far it has traveled. Okay, so pictorially what you're doing is that you're looking at a random variable here and then another random variable there. Okay, that is the meaning of the autocorrelation function. You're looking at the correlation between this random variable and that random variable. For wide-sense stationary processes, you really only care about how far they are apart. You do not care about where do you start and when do you end. Now, this is not the same case as you are looking at here. This example is not a wide-sense stationary process because when you look at one timestamp here versus another timestamp there, their correlation changes over time. Okay, and then it's not just depending on the gap between the two. It actually depends on when do you start and when do you end. Here, for this random process, you do not care about because as long as you fix the duration, you can change. You can look at this pair of random variables. You can also look at this pair of random variables. They are separated by the same amount. Their statistics will remain the same. So for this example is a wide-sense stationary process because it satisfies both criteria. Now, as you can see in this case, since we can write the autocorrelation function as half of cosine omega t1 minus t2, you can also write it as just 1/2 cosine omega tau if you define tau to be t1 and minus t2. So that means I have translated this two-dimensional function into a one-dimensional function in tau, which is a very, very good thing because I can simplify the dimensionality of this problem. So let us visualize this random process in terms of the autocorrelation function. Here is the autocorrelation function of the random phase problem, the second example. It is a two-dimensional function in time t1 and t2. We can draw this diagram, and you can see that you have this bended diagonal structure. So how do I understand it? Well, I can pick any starting point t1 and at any time endpoint t2. For example, I pick t1 to be 0 and t2 to be minus 0.25. So I am looking at this point here. Okay. Now this is t1 equals to 0, and then t2 equals to minus 0.25. This is my first a pair of numbers that I'm looking at. If it is a wide-sense stationary process, I can change my time to any time. Let's say I'm just changing it to 0.5. Okay. And then the gap between this and this, you know that there's a gap of 0.25. So how about I set it to be 0.25? Okay, because this is 0 and it goes back to minus 0.25. And so if I start with 0.5, I have to go back to 0.25, subtract by 0.25. Then let's go back to this diagram here. This diagram says that t1 equals to 0.5, which is here, and then t2 equals to 0.25, which is there. So I go to this point. Okay. So you see that what do I have? The value, this Rx at 0 and minus 0.25 is the same as my Rx at 0.5 and 0.25. Okay. This is the first point. This is the second point. Where are they located? Well, they are located along this diagonal line, and therefore their values are exactly the same. This is what we mean by a Wide-Sense stationary process. The autocorrelation function only depends on the gap. Okay, it does not depend on when do you start and when do you end. It only depends on the gap between your starting point and your end point. If you tell me the starting point, I have to use a specific end point in order to match the distance. So this is a property of the Wide-Sense stationary process. If you have a Wide-Sense stationary process, you should expect to see this autocorrelation function to have this very beautiful structure of a banded diagonal structure, or what we call a toplet structure. Okay, so let me spend some time to describe the physical meaning of this autocorrelation function Rx of tau. Now, the reason I want to talk about this physical interpretation is the following. First of all, calculating the autocorrelation function is really a manipulation of the numbers. That can always be done. Okay. Now, getting a formula does not mean that we know what it is going on. We can even draw the two-dimensional diagram. We may not know what is going on with the autocorrelation function. So what I want to do here is to draw you some pictures specifically about this one-dimensional function, Rx of tau. Okay, no longer it's just the two-dimensional function of t1 and t2. I want to look at a very special case where t1 minus t2 is defined as this gap tau. I want to look at the physical interpretation of this Rx of tau so that we can understand more about what is actually going on. How can we make this useful in practice? So the story goes as the following. We are going to define a quantity called Rx hat of tau. This is like a proxy of this Rx of tau. If you remember what is the Rx of tau, Rx of tau, it is defined as t of x of t plus tau and x of t, and therefore the difference is the tau. So Rx of hat is a proxy to this expectation. I'm going to define it as the integration from minus t to t with 1 over 2t for this entire function. Okay, so this is Rx hat of tau. And what is this function? Well, this function has some very interesting meaning. Okay, this is the temporal average of this product. Right? Okay, why is a temporal average? Well, first of all, you integrate this product from minus t to t, and then you divide by 1 over 2t. So of course you're calculating the average. And because you're doing dt, you're integrating over dt, this is the temporal average. Now this is the statistical average. And here now you're talking about the temporal average. So there should be a gap between these two, and we will address this gap. But for the moment, let us look at what is the meaning of this temporal average. This temporal average, if you look at it carefully, it is very, very similar to another integration that we should be familiar with, which is the integration of this thing. Look, this is an integration of xt plus tau and x of t. Here is x of t minus tau and t. What is the difference between these two? This function is the familiar convolution. Okay, you flip the function over and then you integrate. This is what we call the correlation. Okay, with the tau from going from minus tau to plus tau. That is the difference between these two. So the way to understand this Rx hat of tau is to think as a convolution, but is an unflipped version of the convolution, or what we call the correlation between this function x of t plus tau and x of t. If you try to draw the picture of this correlation versus convolution, you notice that for convolution, you have this function. Let's say you have this red function. As you do the convolution, you need to flip it over, and then you start to shift around, and then you add. That is the convolution. For the correlation, you do not flip over. You just start to shifting the function around. And so what this operation is going on here is that I'm going to calculate the temporal correlation of these two functions. When will I have the maximum correlation? I will have the maximum correlation when I overlap with myself. And then as I travel to the far left or to the far right of the gray functions, I am going to have less and less overlap, and so my correlation becomes weaker and weaker. That is the temporal correlation that we can do on a computer. That's very easy to compute. So what? The magic is that if you take the expectation of this Rx hat of tau, which is a random quantity because you're only taking the integration and division by 1/2t. If you do this, and if you take the expectation of Rx hat of tau, you are guaranteed to get this Rx of tau. This is a random quantity. When you take expectation, it becomes deterministic, and on the right hand side of this deterministic quantity. And therefore, what we're arguing is that the expectation of the temporal average will equals to the statistical average. And here's the reason. If you take the expectation of Rx hat of tau, well, the expectation can go into your definition, and so you have this Rx, you have this x of t plus tau and x of t, and that is exactly Rx of tau. And so now if you try to integrate this function with respect to t, there is no t with respect to your r, and so you can pull the r tau outside, and you just have this integration from minus t to t divided by 1/2t, and so that will give you 1. And so you will have this Rx of tau. And so we showed that if you take the expectation of this Rx of tau, you will indeed get this Rx of tau. So in other words, this thing is the statistical average between this point and this point. Is the expectation, is the joint expectation between two random variables. This is exactly the same as if you take the expectation or the long-term average of this statistics. And this statistics is the temporal average. So what can we say about this? I want to give you one example to illustrate this idea. And this example is the following random process, x of t. This x of t, it has the following property. X of t is an IID Gaussian random variable, variable with zero mean and unit variance. So what does it mean? You have this random process. You go to every time instant. You draw a Gaussian random variable. Okay, so it will be a function like this. At every point, this is a Gaussian random variable. This is another Gaussian random variable. Another Gaussian random variable. They're all independent Gaussian random variables. And so, if you try to calculate the correlation, okay, we want to find what is the correlation between x of t plus tau and x of t. Okay, what we mean is x of tau. What is this? According to the first definition, which is the which is that I'm looking at a pair of random variables here and there. I want to get their correlation. Because they are independent drawn IID Gaussian random variables, then this pair of random variables, they have to be independent, and so you will get a zero correlation as long as they're not at the same location. You can do the same calculation as using this Rx hat of tau. What is this Rx hat of tau? Well, you can take this function. This is your Gaussian random function. You can move it to the left. Okay, the same random function. You can move it to the left to get this one, and move it to the right to get this one. It's like you're shifting this random process left and right, and you try to calculate the overlap between these two, between this function. It is a self correlation. So if you do this, you will notice the following observation. As you're moving around, when you hit yourself overlap exactly, you will get a spike because you get everything is correlated. But as long as you go to the left or go to the right, you have almost no correlation at all. That is because every point is a random variable. It is an independent random variable, and so that you should have no correlation with each other. You can also carry on the calculation as the following. You can see what is the question asks, what is the autocorrelation function Rx of tau? Well, you can plug in the definition. Rx of tau is the expectation of x of t plus tau and x of t. And then the first case is that tau is 0. That means you are overlapping with yourself. You do not have any shift. So when you plug tau equals to 0, you have xt squared. The second case is when tau is not 0. Then in this case, you have x of t plus tau and x of t. But since the independent, the expectation can be written as the product of the expectations, and so you have these two. And now what are these? Well, it is a zero mean Gaussian, and so both of them are 0. And therefore, you can show that this Rx of tau is 1 when tau is 0, and it is 0 when tau is not 0. So essentially, you have this Rx of tau being a delta function. This is your Rx of tau. Okay, so on computer, you can also do this calculation pretty easily. You can go to MATLAB or Python. You can try to generate a sequence of random numbers, and they're all independent, and you plot it over the time. And then you start to do this autocorrelation function. You can use this function xcor in MATLAB, in a similar command in Python. You can try to look at the help section in MATLAB and see what the instructions are, and then you can type in this command and see if you can draw this pattern. Here I'm drawing you two patterns. One is the blue line, the other one is the black line. The blue line and the black line, they are the correlation of the samples of sample 1 and sample 2, because it is a random process, so every time you draw a random process you get a different realization. So is this Rx hat of tau. And then the red function is what? The red function is the expectation over this Rx of tau. So you need to take many of these Rx hat of tau, and you take the statistical average. Then you will be able to get to this red curve. So I will encourage you to try this visualization by yourself. It's a fairly easy exercise in MATLAB and in Python. So the remaining few slides are just some properties of this autocorrelation function Rx of tau. I will just quickly go over them. The first property is that Rx at 0 is the average power of this x of t. The reason is that Rx at 0, you can imagine this temporal averaging function. Since you are overlapping with yourself, okay, so you multiply these two together, you're taking the square of your function, and so that of course will give you the power. Rx of tau is symmetric. That is, Rx of tau will equal to Rx of minus tau, and therefore it doesn't really matter whether you start with T1 and T2 or T2 versus T1, because this Rx of tau is always symmetric. This property says that if you are looking at the probability that x at t plus tau and x of tau, x of t, you are x of tau, and then you check this epsilon. Epsilon is some quantity here. You can always upper bound it by this quantity, which is Rx at 0 minus Rx at tau. Now this property essentially says that the probability of having a large deviation, that quantity is small. The proof is given by here. which I wouldn't go into details, and I think you can read it by yourself. This property says that any autocorrelation function would be lower than the peak. The peak is at 0. That means if you draw any autocorrelation function, no matter how it changes, the peak is always at 0. So I want to mention the last theorem. This is a very useful theorem that tells us how quickly will this Rx of tau converge to this Rx of tau. Now this ergodic theorem is optional for our course, but I will encourage you to take a look. This is the law of large number for random processes in some sense. What it says is that as t goes to infinity, this quantity here, which is the mean of this function y of t, and then if you take this average, so this is the temporal average. This temporal average will converge to the mean value as t goes to infinity, provided some criteria are satisfied. Okay, so what it really means is that you have this temporal quantity. This is the temporal average. You want it to converge to the mean. You ask, how fast can this converge? And this theorem tells you that yes, as t goes to infinity, you will indeed have guaranteed to have this convergence. And then there's a criteria, which is this very technical term here. Okay, so this ergodic theorem tells us when will your temporal average become the same as the statistical average. And that is a very fundamental thing that applies only to Y-sense stationary processes. So as I mentioned, this ergodic theorem is good to know, but it's optional for our course. So is properties like here. It is very good to know these properties, but they are not required. I mean, the proofs of these properties are not required for our course. So to summarize, what have we learned? We have learned a concept called the Y-sense stationary processes. Y-sense stationary processes are a very special type of processes where the mean function is constant. Now, constant does not mean that it has to be 0. You can have a constant of 1. That is also a constant. The second criteria for Y-sense stationary process is that this Rx of T1 and T2 has to be written as Rx of T1 minus T2, so that this two-dimensional function can be simplified as a one-dimensional function using the time difference. If you can understand these two criteria, you will be able to prove that whether one random process is Y-sense stationary or not. There is a very good way to understand this autocorrelation function when it is a Y-sense stationary process, which is that you can view it as the correlation, the unflipped version of the convolution, as the way to look at the temporal average of this quantity Rx. And as you take the expectation of this Rx of hat, you will be able to show that you will converge to the true Rx of Rx. All right, so this is the end of today's lecture. We've gone through some very interesting definitions, and then I will hope that you can try our homework exercise so that you can become more familiar with this concept of autocorrelation function, mean function, and how do we prove whether a process is Y-sense stationary or not. Thank you for watching.